So for our next topic, we're going to return to calculus, and we're going to look now at some of the applications of the calculus. Just a reminder, the first derivative and different notations that we could have, y with a dash or a prime, some people call it, f dash x, d dx, where you actually write the function in the braces, or probably the most common of them all, dy dx. Right? And what we saw was it measures, when we're talking about curves, the slope of the tangent, because the derivative is a rate of change. So we're saying, how does y change as the x value changes? What does that tell us? If the derivative is positive, then we know the slope of the tangent is positive. And if you think of a line that's positive, it means the curve must be rising. So that's a way of telling when the curve is going up or the curve is going down. We can just look at the first derivative to work that out. That therefore means if it equals 0, it's not going up, it's not going down, it's what we call stationary. So just using that very basic idea, we can draw a very rough sketch of a simple polynomial. So y equals 3x squared minus x cubed. We're going to find the stationary points and work out what they are. So dy dx is 6x minus 3x squared when we differentiate. Now, in your working out, you write statements like this, because you're explaining to whoever's reading your solution, why on earth are you solving this equals 0? Well, what are you doing that for? And so you're saying, okay, well look, I'm trying to locate stationary points. So stationary points occur when the derivative equals 0. In other words, I want to solve this equation. And we get two solutions there. Possibility x equals 0, x equals 2. So we have two stationary points. Now, it said determine what they were, what sort of, because a stationary point, you could have what we call a minimum turning point, like our standard parabola over there. You could have a maximum turning point. You could also have a third thing, which is called a horizontal point of inflection. Let's see. So the way of checking it is to have a look at what the curve is doing around that point. Is it going up? Is it going down? So we know it's 0. The derivative was 0, so okay, the tangent's flat. We need to check a point on the negative side, or the left-hand side, and we need to check a point on the right-hand side, or the positive side. And we can pick any number we like, as long as we don't go past another stationary point. So on the left-hand side, there is no other stationary point. I can pick any number I like. But on the right-hand side, I can't go past 2. So I'm going to choose -1 on the left-hand side. When I substitute -1 in, I get -9, and so I know the slope is negative, the curve's going down. On the right-hand side, I'm going to choose 1. I don't have a lot of choice unless I want to play with fractions. And it turns out to be +3, and it's going up. So that's telling me curve goes down, stationary goes up. We must have a minimum turning point. Let's have a look at the other one. Now, as it's a polynomial, logic tells me that the next one should be a maximum one, because it's continuous. But let's just double check, make sure. So there's 2. We want one on the left-hand side, on the negative side, one on the right-hand side. Well, it makes sense on the left-hand side to pick the same one that I've already worked out. So I'll sub 1 in, and we know it's going up. I can pick any number bigger than 2 that I like. I just chose the next integer, 3, and it's going down. So yeah, it confirms what I thought would happen. So 2, 4 is a maximum turning point. The third type I said was a horizontal point of inflection, and that's like our cubic there. So what we would have seen in our table is it would have gone increasing, stationary, but then went increasing again, or decreasing, stationary, decreasing again. So if we saw that pattern, we know we've got a picture that looks a bit like our cubic at that point. Okay, going to draw, as I say, a very rough sketch. So I'll plot in 0, 0, because that's an easy point to find. And 2, 4. Bingo, there it is. That's a very rough sketch. I haven't bothered finding any x-intercepts, but I've got a feel for the shape of the curve. That's just using the first derivative. Alright, so there's a start on this.